Hello students, welcome to our YouTube channel. Today we are going to see the packing of particles in crystal lattice, and in the previous lecture we have seen the constituent particles per unit cell, relationship between density, molar mass and edge length of cubic unit cell, and the problems based on that. And today how the packing of these particles in a crystal lattice takes place. Before that, the constituent particles of a crystalline solid are close packed. In any solid, the crystalline solid, the constituent particles are closely packed and particles are treated as hard spheres, and the closeness of particles increases the interparticle attraction. And now if we see the close packing in one dimension, the atoms are now considered as the spheres, and in the one dimension the spheres align horizontally to each other and form structure like this. And if we consider this particle which is red in color, it has two adjacent particles or neighboring particles, and hence the coordination number, that means the number of neighboring spheres that touch any given sphere, is its coordination number. Hence this sphere has two neighboring atoms in the one dimension, and hence in one dimension if such type of arrangement is there, and it is the coordination number of this sphere is 2. Close packing in two dimension. Close packing in two dimension takes place in two ways, and the first way is these spheres align vertically as well as horizontally, and it is known as square close packing because it forms a square like structure. Spheres align each other vertically as well as horizontally, and the coordination number, if we consider this atom, its coordination number is 4 because it has 4 neighboring atoms or particles which directly touch to it. And in case of another arrangement, if we observe these two arrangements, if this layer is a layer, again this is a layer, again this is a layer, that means it is a type arrangement in two dimension. But in this hexagonal cubic close pack structure, this layer, first layer is considered as A and the second layer is considered as a B, because the spheres fit in the depression of the first row. This is the depression of first row, and the second row spheres are fit in the depression of the first row. Hence this layer is considered as a B layer in case of two-dimensional structure. And here it is very important to note that it has hexagonal close pack structure, and this has a square close pack structure. And if a square close pack structure is packed three-dimensionally, all the layers are A type layer. That means the bottom layer, it is A type, and the layer which fit above it, it is also A type layer, and the layer which is above it, it is also A type layer. That means all the spheres align each other vertically as well as horizontally, and this is the only way by which square close packing structure can be converted into 3D structure. And it is a simple unit cubic cell, simple cubic unit cell, that is a primitive unit cell is formed by square close packing structure when packed in three-dimensional, whereas hexagonal close pack structure can be packed in two types, and we will see these two types. This is a hexagonal close pack structure. We are now here, these are the voids. Some of these voids are tetrahedral voids, and these tetrahedral voids is formed whenever a sphere of the second layer is above the void of the first layer. Now this is the first layer of the 3D structure, and when we put another layer on this layer, the voids are formed, and these voids are tetrahedral voids and octahedral void. This layer is considered as a layer now, and the layer which will be fitted on above this layer will be B layer, though it is a AB type of arrangement. Now it is A layer, B layer, A layer, B layer, but whole layer is now considered as a layer. On this layer another layer above it will be fitted, and it is also in the diffraction of this. That means this is a layer which is black in color, and red colored layer, it is also of AB type, but it is considered as a B layer. And now the black layer is considered as A layer, it is a B layer. And due to this arrangement, this type of arrangement, two types of voids, empty spaces are created, and one is a tetrahedral void. It is formed whenever a sphere of the second layer, this is a sphere of the second layer, and it fits up in the second layer is above the void of the first layer, void of the first layer, and the sphere of the second layer is above the void of the first layer, and this type of tetrahedron is formed, tetrahedral hole is formed, which is known as tetrahedral void. Whereas at the other places we observe that the triangular voids in the second layer are above the triangular voids in the first layer, such that the triangular shapes of these do not overlap. Such voids are known as octahedral voids and are surrounded by 6 spheres, while this void is surrounded by known as octahedral hole, and this octahedral hole is surrounded by 6 atoms, 3 of the first layer and 3 of the second layer. Hence octahedron is formed. That means if we place the second layer on the first layer of AB type of arrangement, the first layer is known as A layer and the second layer is known as B layer, and we see that two types of voids are formed. These are tetrahedral crystal lattice in the three-dimensional structure. Now in the three-dimensional structure we have to add another layer, and if we add another layer, it has 2 types. Before that, formation of tetrahedral holes and octahedral holes due to the placement of the second layer on the first layer. If the sphere of the second layer is placed exactly above the void of the first layer, then tetrahedral hole is formed or tetrahedral void is formed. And if the spheres are placed at the other places, the triangular voids in the second layer are exactly above the triangular void in the first layer, and hence octahedral void is formed, and that octahedral void is surrounded by 6 spheres. These are the different holes which are named as the tetrahedral voids and octahedral voids. Alternately, these voids are formed whenever there are 4 atoms around the hole, it is a tetrahedral void, and whenever there are 6 atoms around the void, it is octahedral void, and alternately tetrahedral and octahedral voids are formed. If n denotes number of particles in unit cell, the number of octahedral voids generated is equal to n, and the number of tetrahedral voids generated is equal to twice n. That means the number of particles, if n, 2n tetrahedral voids are formed and n octahedral voids are formed. In case of BCC structure, if we observe number of atoms per unit cell are 2, hence octahedral voids will be is equal to n, that is 2, and tetrahedral voids will be 2n, that means 4 tetrahedral voids and 2 octahedral voids are there. In case of BCC, you calculate the number of octahedral voids in FCC and the tetrahedral voids in FCC, because the number of atoms per unit cell in FCC are 4. It is a very important thing that the formation of tetrahedral hole and octahedral hole how takes place, so that you have to imagine a layer. In case of a layer, there is also arrangement of ABAB type, because the spheres are fit in the diffractions of the one dimension A layer. This is A layer, this is considered as the B layer, and a whole layer is now considered as A layer, in which the spheres are fitted into the depression of the first layer. And also, if this second layer is placed above the first layer, two types of voids are formed. If the atoms of the first layer have void like this, and the sphere is directly placed on the void of the first layer, then tetrahedral hole is formed. And at the other places, if the spheres are placed, octahedral void is formed. Two types of voids are formed, and this equation is very important. The number of octahedral voids generated is equal to n if the n particles are present in a unit cell, and number of tetrahedral voids generated is equal to twice n. Number of MCQs are asked on the basis of this relation, and we have shown here this the first layer and this is the second layer. The atoms of the second layer are fitted in the depressions of the first layer, and we see the formation of tetrahedral and octahedral layers. Now we have to covering tetrahedral voids. That means we know there are two types of voids are formed if layer 1 is covered by layer 2 in such a way that these do not align each other, because the first layer is considered now A and the second layer is now considered as a B, and covering tetrahedral voids. Tetrahedral voids are formed and these are named as the T. In this kind of close packing, now we have to place third layer. In this kind of close packing in solids, the spheres of the third layer are exactly aligned with those of the first layer. That means if first layer is considered as A and the second layer dark pink, it is considered as B, then the third layer will be light pink and it is exactly aligned on the spheres of the first layer. Hence this type of arrangement is known as AB type pattern, because first layer is A, second layer is B, and again third layer is A. Hence AB type of arrangement, and the structure formed is known as hexagonal close packed structure or HCP. In this we are covering tetrahedral voids like this. First layer is A, second is B, and third is again A. Hence AB type of arrangement, it is known as AB type of arrangement, and the resulting structure is known as hexagonal close packed HCP structure. Now covering octahedral voids. The another type of voids which are present are octahedral voids. In this kind of close packing, the spheres of the third layer are not aligned with those of either the first or the second layer. That means we have to place the spheres of the third layer neither on the spheres of the first or nor on the second layer. That means these spheres of the third layer are placed at the different position. That means these do not align on the first layer or second layer spheres, and this structure results into the cubic close packed structure or face centered cubic structure due to arrangement of ABC. First layer is known as A and the second layer, which is black colored, it is known as B, and C, it is different than A and B because these spheres are placed differently than the A and B, and such a type of arrangement results into the cubic close packed structure, that is CCP, or face centered cubic structure. And hence in both these cases, that means hexagonal cubic packed structure or CCP or FCC, the coordination number is 12. Each sphere is in contact with 12 spheres, and for 74% space in the crystal is filled in this kind of the close packing. We have to remember two types of voids, and the third layer is arranged in such a type that tetrahedral voids are covered and octahedral voids are covered. Like this, three-dimensional structure is formed, which consists of two types of arrangement. These are ABAB pattern and ABAB pattern. If there, this resulting structure is known as hexagonal close packed structure, HCP structure, which is having 12 coordination number. That means atoms or the particles have 12 particles around it. And also in case of CCP, if the octahedral voids are covered, CCP structure is formed, or it is also known as face-centered cubic structure is formed, due to which these two different arrangements are formed. First arrangement is known as ABAB type, and the second arrangement is known as ABC type of arrangement. The fourth layer will be again A type, then B, and then C. Such type of arrangement is known as ABC type of arrangement. Now the coordination number in case of simple cubic, this green atom is at the center, and number of atoms around it, these are 6, and in the same layer these are blue atoms are in the same layer, one above and one below. That means simple cubic unit cell, the coordination number of particle is 6, and in case of body centered, the coordination number is 8, 4 above and 4 below. In case of face centered, the coordination, that means FCC or CCP structure or HCP structure, the coordination number of atom is considered as 12, and the position is 6 in the same plane, 3 above and 3 below. Like this is simple, this is a body centered, and this is a face centered cubic cell. And the question was asked in a NEET examination 2001, when zinc converts from melted state to its solid state, it has HCP, hexagonal cubic packed structure. Then find the number of nearest atoms. That means we have to find the coordination number of HCP structure, and already we have studied the HCP. In the HCP structure, the coordination number or the number of nearest atoms of the atom is 12. Hence the correct answer is C, 12. Now another question, structure of mixed oxide is a cubic close packed CCP. The cubic unit cell of mixed oxide is composed of oxide ions. 1/4 of the tetrahedral voids are occupied by divalent metal A, and the octahedral voids are occupied by monovalent metal B. The formula of the oxide is, we have to write the formula of oxide. Before that, you know CCP structure. In case of CCP structure, it is like FCC. Hence number of atoms or particles in FCC are 4. We have already studied to calculate the number of particles per unit cell, and in case of FCC, because CCP structure resembles with FCC and number of particles or atoms present in FCC are 4, that means there are 4 oxygen atoms, oxide ions are present. 1/4 of the tetrahedral voids are occupied by divalent metal A. That means we have to find the octahedral voids and tetrahedral voids. If there are 4 atoms, then number of octahedral voids are also 4, and the number of tetrahedral voids are 8, because we already studied n is the number of atoms, then octahedral voids are also equal to n, and tetrahedral voids are also equal to twice n. Hence if we see the number of atoms in CCP are 4, because it resembles to the FCC structure. That means 4 O2 minus ions are present. Number of tetrahedral voids 2 into n, 2 into 4, that is 8. Hence number of A2 plus ions, because this is divalent, hence A2 plus, and 8 voids are present, but 1/4 of the tetrahedral voids are occupied by A2 plus. That means 2 A2 plus ions are present, 8 voids. Among these 8 voids, 1/4 are occupied by A2 plus. Hence total number of A2 plus ions is 2, and the number of octahedral voids is equal to number of B ions and is equal to 4, because it is mentioned that the octahedral voids are occupied by monovalent metal B, and octahedral voids are 4, and hence B plus ions are 4. Hence the ratio of O2 minus, it is a 2, A2 plus, sorry, O2 minus is a 4, A2 plus is a 2, and B plus is a 4, 4:2:4, that is 2:1:2. Hence the formula of oxide is AB2O2, and AB2O2, D is the correct answer for this. Like this, we have to solve number of MCQs and very short answer questions on the arrangement of these atoms, ions or molecules in a 3-dimensional structure in the textbook. It is given very complicated. I have here given in short the arrangement of the atoms, ions, formation of tetrahedral voids, and visually it is shown tetrahedral void, where tetrahedral void is formed, where octahedral void is formed, and number of tetrahedral voids and octahedral voids. You have to remember in case of all these, and hence we can solve the number of MCQs. Thank you. We will see the packing efficiency in the next